Hi, welcome back to Petroleum Downstream Crash Course. This is the sixth video, and we are going to talk about desalting today. Now, after examining our crude oil assay by Exxonmobil, we kind of know all the information we need on how to convert crude into our finished product. As we know, crude has salt and some acids, which can cause a corrosion problem. Therefore, we need a desalter to get rid of the salt and acids before we send it to the rest of the refinery. So this is something you just need to treat the crude. Desalter. So I want my acids out, I want my salt out, and also I want some of my metals out and some of the particulate matter. These are solids in the oil that can cause clogging and fouling. So desalting basically does these functions. And how do we do it? Well, the simplest explanation is that we wash the oil with water. So what we do is we take raw crude oil, mix it with water, and rigorously mix it so that almost all the salt of the oil will go into the water. And how much water do we use? If we have 10 liters of oil, chances are we will use 0.3 to 1 liter of water. That's about 3 to 10% volume per volume to extract salt. Now, if you're a chemical engineer, you'll know this is something called liquid-liquid extraction. This is one case of liquid-liquid extraction. So it's good to actually know that kind of stuff. And besides that, you know how much water you need to use? Why do you need to use less water in some cases and more in others? It all depends on the viscosity of oil. Or you can also look at the API value. With higher API values, the less water you need, which means the more dense your crude oil, the more water you need to wash all that salt out. And what else do you actually put in the water to actually get acids, metals, and all this stuff out? Sometimes you use caustic. These are what you call sodium hydroxide or alkali. Some alkali, small concentrations of caustic. And you also have something called a wetting agent. Okay? Wetting agents are basically what tries to get the water sticking onto the particulate matter, like dirt, all of this stuff in the oil. It tries to get it to stick to the water so that it will not come out the treated oil side, but it will be washed out with the water here. Okay? So how much of the caustic do we use? How much caustic? Well, we only want to use enough to neutralize all the acids so that the salt comes out. So that salt is formed, because acid plus alkali becomes salt and water. So the salt, we can come out with the water. So some of the alkali the alkali we use is to neutralize the acid. So how much alkali should we use? Well, our pH range is usually from 6 to 8. We don't want to use too much alkali so that we exceed pH of 8. And why is that so? Not too much alkali. Why? Alkali. Because we don't want a case where oil and water form an emulsion. Now, what is an emulsion? Normally, oil and water don't like to mix. I mean, we get that from everyday experience. But if we put something like soap, oil and water will mix. And why is that so? The soap molecule has a part that likes oil. I love oil here. But the soap molecule also has a part that likes water. Alright, if I add soap to the water and oil, I'll have something like a soap molecule. One part likes water, one part likes oil. So instead of a very clean layer of water and oil, we have these emulsifying agents. So one part of it likes oil, one part of it likes water. And it kind of gets the water to mix with the oil even better, which is not what we want, because we want to get the water and salt out of the oil. So an example of emulsions we know is milk. Milk is a mixture of fat and water. Now normally, of course, it doesn't mix, but there are emulsifying agents that help them mix, with a similar idea, with the fat in this side and the water in this side. Okay, so this is called hydrophilic. Hydrophilic basically means I love water, and this is called the hydrophobic side. Hydrophobic means I don't like water, I'm scared of water. So oil is normally scared of water. So if I have a molecule with a hydrophilic and hydrophobic side, I will have an emulsifier. So what acts like soap in the oil? What acts like soap? My pen. What acts like soap in the oil? You can see my pen's like something wrong. Never mind. I'll try and use it. What acts like soap in oil or crude oil? Well, we have something called asphaltenes and other kinds of resin. And what they have, let's say you have a lot of carbon stuff here, and then we have something like sulfur, maybe a little bit of oxygen, or some carboxylic acid here. Something like that. I'm not sure what's inside, but it's definitely not just carbon and hydrogen. You have other stuff like this as well, and you even have metals in there, in what is called an organometallic compound. Now when you introduce alkalis into these asphaltenes, well, there's going to be other stuff here. I'm not going to draw everything out. Yeah, if you introduce alkalis, like sodium hydroxide, the thing here, so this R is going to be the rest of the stuff. The thing here is that you form a salt part. So this part is hydrophilic, but the rest of the asphaltene or resin or whatever it is going to be hydrophobic. So this is a lot like what we have up here, where we have a soap that likes water, the hydrophilic part, and the part of soap which doesn't like water, which is the hydrophobic part. So asphaltenes act as natural emulsifiers. So we need to keep the pH at 6 to 8. But sometimes, even keeping pH at 6 to 8, the emulsion still can form. So to prevent this, so even at pH 6 to 8, you still have emulsions. So how do we prevent this? We have special chemicals known as the demulsifiers. Demulsifiers or de-emulsifier, something like that. Yeah. So what this chemical does is to try and prevent all these from happening. So the water will stick with water and the oil will stick with oil. So in a desalter, let's say a mixing tank, have some water, some oil, and some demulsifier. So you want to have a settling tank or decanter to separate two phases of liquid which cannot mix. So the oil will come out on top, the water, the emulsifier, and salt, etc. will come out the bottom. Okay? So what do we have now? Well, from here to here, after you mix it up with this stirrer or something like that, you have to agitate this mixture. You're gonna actually have a situation where you have a lot of oil and you have tiny droplets of water inside. So all these droplets of water, which is the water phase. And if you're going to wait for all these droplets to drop to the bottom, just by gravity, if you're going to wait for it here, it's going to take ages. So how do you speed up the process? The first thing you want to do is to actually unthicken the oil. And how do you unthicken the oil? You can unthicken the oil with a very easy method or technique. You just need to heat it up. So you just get a new pen, heat it up. And why is that so? Well, let's take a look at our assay again. And we can look at the viscosity at around room temperature of crude oil, which is about 50 centistokes. Here at 20 degrees centigrade or 20 degrees Celsius is about 57.3 centistoke. 40 degrees, it's about fever temperature, your body having a fever. That's about 24 centistokes. And you see, as you heat up the oil, the viscosity decreases. And if you heat it up beyond 100 degrees, you see this viscosity of oil drops by almost 10 times. So at 20 degrees, you increase 80 degrees of temperature, you have a drop in viscosity of around 10 times. At 150 degrees, even less, 2.3. So that's how you unthicken the oil. Use heaters. So we keep the oil at around 90 to 150 degrees so that the viscosity is 2 to 5 centistokes. And that's not too bad. Now, the other way to speed up and let the water droplets grow in size is to use electrostatics. So we have maybe about, let's just put the upper limit, 150 Cs. So the oil is a lot less thick, but the water droplets are still small. How do we get them to grow in size so that they'll drop even faster? The way to the way to make the water droplets grow is to use electrostatics. So you apply an electric field here, and what happens to the water? Let's zoom in. Let's put like 3 drops, and the electric field is this way. So this is a plus and minus. So these water droplets will start having charge. Minus to the left, plus to the right. So you see, opposites attract. When you have positive, the negative part tends to stick to the positive. So you can see there's a negative part of the water, positive part, they'll stick together. Negative part, positive part, stick together. So with this electrostatic attraction, the water droplets grow in size. And when they're big enough, they'll start dropping faster and faster. So they'll start having a layer at the bottom where you can take off your water. The other way you can do it is to use an AC current. Okay, so if that is oil and there are some water droplets inside, AC current basically flips its polarity like 50 times a second, but the point is that it alternates. It alternates quickly, and what happens is that these guys start vibrating a lot. So when you have vibrating particles, they're more likely to contact each other. And when they can contact each other, the water droplet size will grow. So when the water droplet size grows, it's the same idea. Water droplets will sink to the bottom, and at the bottom you can collect your water effluent. And at the top, you can collect treated oil. That's after all these things have settled. So yeah, settle to the ground, and yeah, that's it. So let's draw an overall diagram of the desalter. So we have raw crude oil. We have water and caustic, which is the alkali I was talking about. And we have demulsifiers as well. And we put all these into a mixing tank. Or rather, hold on. We need to heat the crude oil up first. Let's redraw again. We need to heat the crude oil up first to about 90 to 150 to unthicken the oil. And we have water. We have demulsifier. And then we have caustic. Just a small bit to neutralize all the acids. So this is where you mix everything up. And then you have your electrostatics here somewhere to help the water settle down. And what you get is water effluent and treated crude oil. And this is what you actually send straight into your distillation column. Now that's all I have for you. I have an exercise. So this is your homework. Again, please post it in the comments. How thick is crude oil with respect to honey and water. So I want you to compare the thickness or viscosity of crude oil with respect to honey and the viscosity of crude oil with respect to water. So thanks for watching. I'll see you next time. Bye.